All right, here's our third video in section 5.4. We just got done talking about perfect squares. Now we're going to talk about what we call difference of squares. And if you remember from our 7 steps of factoring, anytime I have two terms, it's either going to be factored, hopefully, with either a difference of squares or what we call cubes. We'll talk about that later in the next section. But difference of squares happens when I have two terms that are being subtracted. It has to be a difference of squares. There is no such thing as sum of squares. So it has to be a minus sign in between my two terms or else it won't work. Also, my coefficients or my numbers, my constants, must be perfect squares. For example, 1, 4, 9, 16. You notice that all of these are squares. 1 squared is 1, 2 squared is 4, 3 squared is 9. We want to make sure that all of our numbers are perfect squares. They're square rootable. I don't know if that's a word, but we should be able to break them down by taking their square root. Also, if we have any variables with exponents on them, we need to make sure that those exponents are even so we can break them down equally. So like a t squared can be broken down into a t and a t, or an x to the 6 can be broken down into an x cubed and an x cubed. We should be able to divide those exponents by 2 and spread them out equally. If those things happen, we have two terms, it's a difference of squares, we can take that difference of squares and factor it into two conjugate binomials, meaning one has a positive sign between and one has a negative sign in between. We kind of saw that at the intro video of 5.4. Let's do a few more examples of that. So in order to factor using a difference of squares, one, we're going to rewrite our terms as squares. So any number we're going to take the square root of, and any exponent we're going to divide by 2, so we can break up each term equally. We need to then make sure that our bases of our squares go into conjugate binomials, one being positive and one being negative. Let me show you. Looking at example number 3, it asks us to factor. So we still have to make sure that we follow those 7 steps. Number 1, is it in order? Number 2, is there a GCF? And if you look, this one has 2 terms now. So if there's 2 terms, we're either going to try to do a difference of squares or we're going to do cubes. So let's try difference of squares. So can we take this 4 and square root it? Is that a perfect square? Well, yeah, the square root of 4 is 2, right? And can we take this x squared and divide that 2 by 2 equally? Can we break that up equally? Well, sure, I can put an x and an x, right? So what I can do is factor this into 2 conjugate binomials. I can put an x in the first one, I can put an x in the second one, and then I can take the square root of 4, which is 2, and separate them, one with a plus sign and one with a minus sign. You can double check, you could double check by FOILing it out and making sure you have the same answer. I'm not sure why that keeps deleting, sorry. So if I were to FOIL it out, x times x is x squared, x times negative 2 is negative 2x, 2 times x is 2x, and 2 times negative 2 is negative 4. And you notice that these two middle terms are opposite, and so they end up zeroing each other out. So I end up just getting 2 terms, and x squared minus 4, which is what I started with, right? Or if you think about it, like I said in the intro video, there might be a missing term in the middle. If I were basic factoring it, what 2 numbers multiply to negative 4, when you add them together, you get nothing. You get a 0. Well, you should say positive 2 and negative 2, right? That's a difference of squares. There's 2 terms, there's a subtraction sign in between, and I can break each term up equally. Let's look at B. B is in order. I don't think there's a GCF, right? There is no number that divides into 25 and 9 equally. So there's no GCF, and I see 2 terms. Now, are each of these terms perfect squares? Well, sure, what's the square root of 25? And can I take that x squared and break that down? So I can put a 5x in the first one. I can put a 5x in the second one. What's the square root of 9? 3. So I can make one negative, one positive, and I've just factored it using a difference of squares. I have 2 binomial conjugates. You can double check by FOILing it out, but you should end up getting 25x squared minus 9. Let's do another one. All right, I have a 16m squared minus 49p squared. And it's kind of in order. Is there a GCF? Is there a number I can take out of 16 and 49 equally? I don't think so. And it looks to me like there's two terms, so let's see if this is a difference of squares. Well, I notice that there's a subtraction sign in between. And is 16 a perfect square? Is 49 a perfect square? Can I break down an m squared equally and a p squared equally? So let's see if we can break this down using our difference of squares into two conjugate binomials. I took the 16m squared and I broke it down into 4m and 4m. And then I took the 49p squared and I broke it down into a 7p and a negative 7p. They are conjugate binomials. This would be another example of a difference of squares. Let's keep going. Ooh, look at D. D, kind of in order. I guess it's kind of hard to tell when you have different variables, but I like it in this order because I like the subtraction sign in the middle. If there are two terms and there's a subtraction sign in the middle, I want to see if I can separate this using my difference of squares. Now, is each term a perfect square? Well, can I take that s to the 6 and break it down equally? Another way of saying that is, can I divide 6 by 2? Well, sure. I can put an s cubed in one and an s cubed in the other parenthesis. Now, is 16 a perfect square? And can I break t to the 10th power up equally? Well, what's 10 divided by 2? 5, right? So I can put an s cubed in each parenthesis. I can put a 4t to the 5th in each parenthesis. And because that's a minus sign, I can separate them as conjugate binomials, one positive and one negative, and I would end up with the right final answer. That's another example of difference of squares. That's why I didn't rearrange it, so that I can make sure that I have the negative sign in between. All right, look at E. It's in order. There's no GCF, and there's a minus sign in between those two terms. Let's see if this is a difference of squares. Can you take an x to the 4th and break it up equally? Yeah, let's put an x squared in one and an x squared in the other one. Now, is 81 a difference of squares? AKA, what's the square root of 81? 9, right? So I can actually do two conjugate binomials here, and I can say I have an x squared plus 9 and an x squared minus 9, right? All right, hopefully you didn't stop there. Hopefully you're looking really carefully, and when I ask you to factor, you factor all the way down as far as possible. I want you to look at this second binomial. Do you see how both of those are still perfect squares? Can I take the x squared and break it down? And can I take the 9 and break it down? So I should be able to break this down a little bit more, factor more into an x plus 3 and an x minus 3, right? I want to factor all the way down as far as possible. Now be careful. Look at this first binomial. Is that a difference of squares? Now the x squared can be broken down and the 9 can be broken down, but because there's a plus sign in between, that is not a difference of squares, and you can't break that down even more. Think about that. If I have an x squared plus 0x plus 9, tell me if there are any numbers that can multiply to a positive 9 that add to nothing. Well, if you tried 3 and 3, doesn't that multiply to 9? But it adds to 6, right? And so that wouldn't work. Or if I did negative 3 and negative 3. If I did negative 3 and negative 3, that would multiply to 9, but it would add to a negative 6. And if I did 1 positive and 1 negative, that would give me 0 in the middle, but what would it multiply to? Negative 9, right? So that doesn't work. So that's why it has to be a difference of squares. It has to be a minus sign in between in order for it to be factored using the difference of squares. So this would just be my final answer. I have my x squared plus 9, that can't be factored anymore. And then I have my x plus 3 and my x minus 3, making sure that I factor all the way down as far as possible. Don't let me get you on your homework and your test, okay? So make sure you're looking out for that. All right, let's look at F. Is it in order? Ooh, let's see. How many of you guys wrote it in a different order? You can do that. You can make the negative 8x to the 8th plus 50x squared so that it's technically in order. Then what did you do? Hopefully you looked for a GCF. And if that leading coefficient is negative, you GCF'd out a negative 2. I took out a negative 2 and an x squared. You should always, always, always make sure you're following those steps. Put it in order and take out a GCF before you do anything else. When I took out that negative 2x squared, I had a 4x to the 6 minus 25 left over. My leftovers had two terms, and I want to try to see if I can factor even more. If there are two terms and no other GCF left, let's see if this is a difference of squares. Well, I notice there's a subtraction sign in between, Is 4 a perfect square? Is 25 a perfect square? And can I take the x to the 6 and break it down equally? Looks like yes, yes, and yes for all of those, right? So let's break that down into two conjugate binomials. Let's break the 4x to the 6 down into a 2x cubed and a 2x cubed. And let's take the 25 and break it down into a 5 and a 5, one positive, one negative, and then don't forget about your GCF in the front. I don't think that can be broken down any more because 5 isn't a perfect square and 2 isn't a perfect square. So it looks like that's our final answer. But that's another example of a difference of squares with a GCF in there. All right, make sure that you practice your difference of squares because we're going to add to it in a little bit. And then we even have to throw in one more factoring technique of cubes. And we have sum of cubes and difference of cubes.